To summarize what we have covered in this chapter, we are looking at current and resistance, where current is the rate of change of charge, or charge flowing over time, so we also identified the current in terms of the current density. The current density being the current per unit area. The number of charges flowing per unit area per unit time, and so that has a vector. It's a vector, and when we look at an arbitrary surface, we need to mind the orientation of the current density relative to the normal to the surface. The current density is related to the drift velocity and the charge carriers by this expression, as we derive. This is the charge of the carriers, the number of carriers per unit volume, and the drift velocity. That's the relationship between those two. We have the current is, or rather the resistance is defined as the ratio of the voltage applied to the current flowing through a particular material. Now so making measurements of voltage versus current gives us the value of the resistance. So we can have materials that have different resistance, different values of the resistance for different voltage applied. Those are materials that do not obey Ohm's law, and so in general, this guy is not a constant. It's a constant for ohmic materials, for materials that obey Ohm's law, where the current, where the voltage and the current are proportional, and the proportionality constant is the resistance for those materials. We also introduce the resistivity of a material, which is a local property, as is the resistance per unit volume, sort of, or resistance per unit length. In this way, the resistance is the resistivity of the material, which is a function of the temperature. So when you look it up in tables, you find always reference to a particular temperature value, say 20 degrees. The length of the material and the cross-sectional area of the material. So if you are interested in finding the resistance of a chunk of a length of cable of copper, then you look up the resistivity of copper, you know the length of the cable, the cross-sectional area, and then you can determine the resistance of that particular length of cable, of copper cable. The resistivity is again a function of temperature. Over some temperature span, the resistivity can be, as a function of temperature, can be approximated by a linear relationship in this fashion. This is the resistivity at some reference temperature T0. At a different temperature T, the resistivity is going to be the resistivity at temperature T0 times this factor, where alpha is the temperature coefficient of resistivity. Okay, and so alpha has dimensions of inverse degrees centigrade or Kelvin. And there is in the same way that for ohmic materials, the voltage is related to the current. V is equal to Ri for ohmic materials, right? So then in this case we have V equals Ri. We can also find a relationship between electric field, which is the cause of forcing carriers to move, and the current density. So the electric field is the resistivity times the current density. So this represents a local property in a given material. If we know the electric field at a point in the material and know the resistivity of the material, then we can relate the current density to that electric field. We also look at the fact that a resistor will dissipate heat, and if we supply this much power, so we have a voltage source supplying this much power, IV, then and we look at the voltage across a resistor. That resistor is going to dissipate that power as heat, and the power dissipated by the resistor, if we use Ohm's law, say we replace V to IR, then we'll get the power dissipated by the resistors is I square R, or if we substitute for I, we would get V squared over R. Now, the use of either one of these depends on what conditions we have. If we have a fixed current and we want to determine the power dissipated by the resistor, so we use this guy. If we have a question where the voltage is fixed, then again we would use that one. Okay, so it is driven by the input, what expression we use. Just one more thing that I think the book talks a little bit about, and that is there are materials where the resistivity, where when we increase the temperature in a conductor, when we increase the temperature in a conductor, the resistance goes up, and that is because as we increase the temperature in the conductor, the lattice sites, the places where the ions are fixed, those sites are oscillating with larger displacements. Okay, and they are random. So the electrons that are being moving about by due to the presence of an external voltage are going to be finding more collision spots. The cross-sectional area of collision increases by having the temperature increase. So in a conductor, the resistance drops as a function of increasing temperature. In a semiconductor, when the temperature promotes electrons that are in what is called the valence band, which is they don't move, to a conduction band where they cannot move. And so in a semiconductor, the resistance drops down as a function of temperature. There are other class of materials called the superconductors, and we won't do much with them except to notice the following. In a superconductor, we have the following behavior for the resistivity. So if we look at as a function of temperature, okay, one would think that as a function of temperature, materials would reach as the temperature, absolute temperature. As the temperature goes to zero, the resistivity goes to zero in some fashion. Okay, so most materials would do that. Or if there are some impurities in the material, then it doesn't matter how much that we go to absolute zero, we will still have encounters of those moving electrons with the impurities. So we could have a condition where the resistivity goes like that. It reaches a finite value even at zero temperature, and that actually can be a way to quantify the impurities in a conducting material. In a superconductor, it happens that the resistivity actually goes to zero at a finite temperature. Okay, the transition temperature, the superconducting temperature. Below this temperature, there is no resistance for the electrons to flow. Those are the superconductors. This was discovered by Camerlin Owens, actually. His student, and he was looking at properties of some metals at very low temperatures, and Camerlin Owens was the first to liquefy helium. Helium goes liquid at around 5 degrees Kelvin, and So he used liquid helium to explore the properties of some metals at very low temperature, and the observation was that, you know, as the temperature was going down, there was a point where the material, the student was studying the resistivity of the material. As the temperature goes down past a critical value, the resistivity would go to zero. So he reported this to the student, that is, to Camerlin Owens, reported that. And Camerlin Owens said, no, you go back and repeat the measurement. And, you know, working with cryogenics is pretty hard. So repeat the measurement. You know, it was not just a simple ask. So after several trials, Camerlin Owens finally went down to the lab. You know, the lab for Camerlin Owens is in the basement of the Leiden University in Holland. And that's, it's been preserved. Actually, lectures are held there in the lab of, former lab of Camerlin Owens. In 1908, that's when all this happened. And so finally, Camerlin Owens convinced himself that that was the correct measurement, and then he published that and became famous, got the Nobel Prize for his discovery of superconductivity. This is again how resistivity plays a role in defining the properties of the material. So we have conductors, superconductors, and semiconductors. That's and then we have isolators. They conduct nothing. So that is what we've seen in this chapter. Now let me show you few more demos that sort of like connect these last ideas: losses, heat losses, and resistivity. Okay? Yes, please.
In the book, it talks about drift speed moving in the direction. It actually says drift speed moves in the direction opposite of the applied electric field. And then a paragraph below it, it says drift speed moves in the direction of the applied electric field.
Okay, so for the electrons would move in the opposite direction as the applied electric field.
Okay, because there's a picture that actually has it moving in the same direction. Like right below.
Okay. So we, so remember this picture, let's see. This very first picture I show you. We have the electric field, right? The electric field pointing in that direction, negative carriers move in the opposite direction as the electric field. That would also be the direction of the drift of the electrons. And however, the current density is in the same direction as the electric field. Okay? So if we then relate the drift velocity connected as a vector with the current density, they point in the same direction, right? In the direction of the current flowing. What we need to then mind is the sign of the charge, okay? But this is the picture. We have the electric field in that direction, negative carriers going the opposite direction, positive carriers going the direction of the electric field. Okay, does that clarify it?
The charge. I'm just not sure if the book's wrong or if it's a mistake or if I'm just not understanding the concept. Because I understand that. I'm just
okay.
in the book under drift speed, I don't understand.
Okay, let me find it. What you know what
49.
what figure is that?
749. It's 46-2.
749. Okay. All right. So, what are we looking at?
So where it says bolded drift speed,
So this figure is clear, right? Electric field, drift velocity, current density.
In the same direction.
Positive charges, right? And then you have another picture that seems to contradict that.
So it says drift speed is in the direction opposite that of the applied electric field.
For the electrons.
Okay,
For the electrons.
Okay. That was my question.
So if you look at the electrons going in the opposite direction of, if you label them, and then measure the average velocity of that label, that tag electron, that is going to be its drift velocity, and it points opposite to the electric field. Okay. Does that clarify it now?
Yes, thank you.
Thank you. Okay, so let's go now to these demos. The first one is the comparison between carbon and tungsten lamps. So where the filament is carbon in one and tungsten in the other, and what this video clip shows is the behavior of the current as a function of voltage.
These two light bulbs with filaments of tungsten and carbon will be used to show two different ways in which resistance changes with increasing temperature. We'll apply increasing voltages to each bulb in turn and plot the current that flows versus the voltage as each bulb gets hotter. Here is tungsten at 25 volts, 50 volts, 75 volts, 100 volts. Here is a carbon filament at 25 volts, 50 volts, 75 volts, 100 volts. This graph shows the amount of current that flows through each bulb as the voltage is increased. The resistance of the tungsten bulb increases with increasing temperature, but the resistance of the carbon bulb
decreases with increasing temperature. That's what he was going to say. But I wanted to stop on that one. So let's see. So this is current versus voltage. So when we look at the local slope of this curve, the local slope will be the inverse of the resistance, right? Right? Current versus voltage. And so as we look at, the voltage increases, the slope for tungsten is going down. That means the resistance is going up. Yes? And on this curve for carbon, notice that the slope goes up as a function of voltage. That means the resistance is going down. Okay? So the resistivity, the behavior for each one of those is different as a function of temperature. One is a conductor, the other one is not. Okay? Semiconductor. Okay. So let him finish that.
increases with increasing temperature.
Okay. Okay, this is just for fun. It's a hot dog frying. You can do that at home. Plug your hot dog on the directly to the wall.
We'll skewer this hot dog onto two nails and run a current through it to show the heating produced by the current. 110 volts are applied to the nails, and a current begins to flow through the hot dog. After a few minutes, the hot dog begins to steam from the heat produced by the current.
I don't know if I would eat that hot dog. But it was a fast cooking, huh? So this connects to the I square IR square losses, I square R losses.
When a current flows through a wire, heat is generated. We'll use these two different wires hooked in series to show how the amount of heat generated depends.
So the fact that they are connected in series means that the current that flows through each one of them is the same, okay? Otherwise, there will be charge accumulation, okay? So it's the same current flowing through both of them, but they are two different materials. And I don't remember which, well, he's going to tell us.
On the resistance of the wire.
Oh,
this
copper.
wire is made of copper, a low resistivity metal, while this wire is made of nichrome, a metal with a relatively high resistivity. We'll put a paper rider on each wire, then run the same current through both wires to see which heats up the most.
Nichrome has higher resistance than copper.
The nichrome wire burns its rider almost immediately, but the rider on the copper wire isn't even scorched.
So what is same current? Remember, same current. So the losses are to understand that particular demo, we have to look at this expression for power dissipated. Right? It's the same current for both of them. The copper has a lower resistance than the nichrome wire. So the amount of heat dissipated by nichrome is larger than the one dissipated by copper. Okay? And this is just a warning for you guys that for some of you guys, or maybe some of the people that you know that connect too many appliances to the same outlet. That's a bad practice. So this one.
Have you ever seen your house lights dim when you turned on a heater or a heavy appliance? We'll use this model of house wiring to demonstrate the effect. Two resistance wires will substitute for the normal copper wires used in a house to increase the effect. They run ordinary household current into this bank of lamps and heaters, which can be switched on and off individually. We'll first switch on the lamps. Then heaters will be switched on one at a time. When enough heaters are added to the line, the lamps dim. The electrical energy lost in the wires which deliver the current is dissipated as heat.
Okay. Pick a different outlet. that is not connected to the other one. Okay. Let's develop a little more insight then into this chapter by looking at some of the questions.
Sir?
Yes?
Question about the I squared R. So because those two were connected in series, they had the same current, you'd use I squared R. If they were connected in parallel, they would have the same voltage, would you use V squared over R?
Yes.
Okay.
Yes.
Thank you.
So yeah. That's how to view the problem. By the way, I gave you a question for the homework, right? That the question is, why do we use high voltage for transmission lines, right? Transmission lines have long distances, right? So if you have a fixed power source, say the hydropower, that's the dam power, and then you are transmitting this over long distances. If you use that expression V squared over R and replace R for its, in terms of, the wires that you're using are copper wires. So, and long, they are very long copper wires. So replace R in terms of its resistivity and length, and you'll see that larger voltages travel longer distances. Okay, that's why at the source we have these humongous amounts of voltages, right, in the thousands, and then we step them down as they come into the households. And we'll see also why the combination of those two is fairly effective. If we have a source far away, the best way is to have high voltages that are alternating, okay, AC. If they were very close by, then distance is not an issue anymore, and you can have DC sources. But because of the separation between the source and the users, we use alternating voltages that are at the source are very large. So you can convince yourself by playing with that relationship between V squared, the power, and V squared and over R. Okay, so let's look at some of these questions. Okay, so we have the first one. Okay, the first one is we have 3 different conductors, and they have it's such that we can fit this over here snugly, and we can fit this guy over here snugly. Okay. And we want to rank these conductors according to their end-to-end resistance. So we're looking at the cross-sectional area. So they all have the same length, okay? They are coming out of the board, but they have these different shapes, okay? So we want to rank, according to the end-to-end resistance grade first, the individual conductors, the combination AB, that meaning B inside A, and the combination BC, that means C inside B, and then the combination ABC. Okay. So how do we approach this problem? We're measuring resistance, and we want to rank the value of the resistance according to those combinations. So what do we need to pay attention to?
R equals rho L over A.
Right, so the length is fixed. There is the same material, so we need to pay attention to only the area in this case, okay? So let's calculate those areas, right? We have what is the area of this first guy? L squared, right? Because it's the area of the outer cube, which is 3L squared, but then we are removing that much to L squared, so that is L squared, right? That's the area of the first one. What is the area of the second one? Huh? L squared, okay. And the area of the last one is L squared. So ABC, individually, they have the same resistance, right? Now, when we do the combination B inside A, okay, so when we move this guy over here, then the area increases, obviously, right? So what is now the area? 2L squared, okay. So that would be 2L squared. And when we move this guy inside here, the area is also 2L squared. Okay, so that the BC and AB combination, they have the same area. So they have the same resistance. Now, when we have everything together, the final area will be simply 3L squared, right? If we put now this guy in here, that area will be 3L squared. So the lowest resistance is the combination ABC, followed by AB and BC, followed by A and B and C separately. Okay? Are we good? Okay, so we kind of like the same idea here. We have same material, different cross-sectional areas, and we want to rank the resistance according to end to end. And so the only thing that matters is the area, right? So this has the least area, followed by that one and then that one. Okay, so that would give us this has the highest resistance, followed by that one and that one. Okay. This is an interesting one. We have this chunk of material has those dimensions, L by 2L by 3L, and a potential difference is applied respectively between the pairs of opposite faces, between left-right first, then between top-bottom, and then between front and back. Front and back, sir. Okay, the same potential. And so we want to rank these. We want to rank the following: the magnitude of the electric field, the current density, the current, and the drift speed of the electrons. Okay, so how do we do this? So we want, let me actually reduce the size of this. No, I can't. So I need all those things. So let's do it like this. Let me bring it down. And now I have space here. So we have left-right combination, and then we have top-bottom, and then we have front-back. Okay, it's the same voltage. Okay, and the first thing is the electric field. The electric field would be the applied voltage divided by the corresponding length, right? So left-right has an electric field which is the voltage divided by 3L. Top-bottom, the corresponding length is L, so the electric field is V over L. And front and back is V over 2L. So the highest electric field is this one, the top-bottom, followed by front-back, followed by left-right. Then, the magnitude of the electric field has that ranking. The current density, how would you, if you know the electric field, then you can rank the current density, right? It's the same, we're dealing with a material where the resistivity is not changing. It's the same. So the current density this would be then number 1, that would be number 2, and that would be number 3 in ranking, right? Because they are proportional, okay? It's the same resistivity. We're dealing with the same chunk of material. What else? The drift velocity. The drift velocity. So the carriers have the same charge. The number of carriers per unit volume is not changing, right? Unless we have a material that is anisotropic, but we are assuming that this is isotropic. So the number of carriers per unit volume is the same. The electric charge is the same. So the only thing that we see to compare is just that the current density is proportional to the drift velocity. So again, we would have 1, 2, and 3. And what else? The current. So the current, we know what the current density is doing, okay? The current, remember, is related to the current density by the area, right? So the current density is the current times the area, okay? If we know the current density, we know the current. So or if you wish, we can simply see how the resistance scale. Why don't we do that? The resistance. No, that's too much. That's too much work. Let's do current density. So the area seen left, right. The area seen is L. So let's do the area. The area is 2L squared. Over here is from top bottom. The area seen is 6L squared, and front back the area seen is 3L squared. So the current, if we have a fix on the current density, notice something that so the current I, okay, would be how the current density scales, but the current density scales in this fashion. Okay, it scales like the field, right? So the current density the current would be the current density, which is V over 3L, about V is proportional to V over 3L divided by the resistivity, times the area, times 2L squared. Then for the second one would be V over L times 6L squared, right? And then for the last one would be V over 2L times 3L squared. So you have 3 halves, 6, and 3 halves. So for these two is the same, and for this one is the largest. Okay. How much material you're exploring gives you a sense of the current, the actual current flowing.
You're saying the current equals the electric field times the area.
No, I'm not saying that. I'm saying it's proportional to that. So then more precisely would be that. Okay? Are we good? Yes? Okay? So we have now, these are plots of current as a function of time. Okay? And the question is to rank these periods, these bursts of current, in terms of the net charge that passes through the cross section during the period, greatest first. How do you start thinking about that problem? So you're given the current as a function of time. So you want to know how much overall charge we have in each one of those bursts of current. How do you get that? So the current is the derivative of the charge with respect to time. So the charge should be the integral. So we need to look at the area under the curves. Okay? So this has 2 units by 1 unit. This has 1 unit by 2 units. That's still the same number. And this has 2 units by 2 units divided by 2. So these 3 guys have the same area. And the net area for this one is 0. So these 3 have the same charge, and the net charge over here is 0. Okay, so we have 4 situations in which positive and negative charges move horizontally, and they give the rate at which each charge moves. Okay, so we have this for A, this is B, that is C, and that is D. Okay, so on the first one we have 7 coulombs per second. What do we have on the second one? So we have positives moving that way, negatives moving that way. So what is the net current? 7. So these 2 are the same. Well, how about this one? It's the same. So these 3 are the same. And this is an awkward. I don't that's unphysical unless they are free to move. So that would be a 5, right? Not a 7. But well. Okay. So we have this wire that has three sections that they are changing its cross-sectional area. So okay, it's a pipe. And we want to rank the sections according to the following quantities, greatest first. The current. So these are the A, B, and C. Does the current compares on A relative to B relative to C? Should be the same. Otherwise, we would have charge accumulation. Okay, so current has to be the same. So current is the same. So then what changes? The magnitude of the current density and the magnitude of the electric field, right? If the current is the same, but the cross-sectional areas change, the current density changes. It's highest here on the shortest, right? Remember, current density is current per unit area. So it's highest here, and then there, and then there. Okay? And the electric field, being proportional to the current density, would also be high here, then there, then there. We have the electric potential as a function of position along a copper wire that carries current. Okay. The wire consists of 3 sections that differ in radius. That's why you have a change in potential. And we want to rank the 3 sections according to the magnitude of the electric field and the current density greatest first. So the 3 sections are A, B, and C. So we look at the electric field, then we can get the current density because they are proportional. So what do you see? Which one has the largest electric field, the largest magnitude of the electric field? So what is the relationship between electric field and potential?
Potential is the integral
So the electric field is,
of the electric field.
the electric field is slope, the slope of the potential, right? The gradient of the potential is the electric field. Which one has the largest slope? So it's B, then A, and then C. Okay, this is the one. We have so this table gives the lengths of 3 copper rods. Okay, 3 copper rods and their diameters and the potential difference between the ends. And we want to rank the rods according to the magnitude of the electric field within them, the current density within them, and the drift of the electrons through them. So that is we will be repeating ourselves, right? Because electric field is proportional to current density, and current density is proportional to drift velocity. So once we rank the electric field, we ranked all 3 of them. Okay? So that's what we need to do. The electric field, this is the length, that's the diameter, and that's the potential difference. For the electric field, what matters? We know is the potential difference is applied across its length, across the length of the wires, the 3 rods. Okay, so the electric field only cares for that length, right? V over L. The electric field is the gradient of the potential. And so we don't care about this. It's just the electric field would be V over L on the first one, would be V over L on the second one, and would be 2V over 3L on the third one. So that ranks the electric field. We would have that the first 2 have the same electric field. They are the highest, and then the third one is the lowest. Okay. Then the corresponding current densities are also ranked that way: high equally, and low. And the drift velocity will be higher for the first 2 than for the third one. Okay. So electric field is the gradient of the potential. So we're only interested in the length. If we want to know the resistance of the rods, then this is an important parameter to look at, right? Because the resistance of the rods is going to be determined by the length and the cross-sectional area. This is the drift speed as a function in copper as a function of position on the wire. So the wire consists of 3 sections that differ in radius. And we want to rank the sections according to the greatest quantities first. The radius. Okay, first the radius. So we have the drift velocity as a function of radius. As a function of position, and so we want to know which of these 3 sections has the largest radius. So what is constant here? So there is a flow. There's a flow of charges. So what is along the wire that has varying radius? What is constant? The current. The current is constant. Current is constant. Okay? But the current density is not. The current density is current per unit area. So largest areas would have lesser current densities. So which one is the biggest radius? C, then B and A. Okay? number of conduction electrons per cubic meter. The number of charge carriers per volume. It's the same, right? Because it's the same because it's, anything per unit volume represents a local quantity, right? So it does not depend on the overall system, but local. So the number of carriers per unit volume is the same in A and in section A, section B, and section C. And then the magnitude of the electric field. So we have the drift velocity. We have the drift velocity. We have the current density. They are proportional. Then the electric field is proportional to the current density. Which has the highest electric field? What section has the highest electric field? So the drift velocity and the current density are proportional. Okay. So this would have the highest current density. Next one. Which one has the highest electric field then? A. Okay. So and the conductivity. The conductivity is the inverse of the resistivity. So which one has the highest conductivity? They are the same. It's this, again, it's a local property. Resistivity is a local property. Okay, so we'll wrap up tomorrow.